the outline of my talk, I will give you first a short reminder on phonons, and then I will focus on phonons on disordered materials, and in particular on the impact of elastic fluctuations in their propagation. Finally, we switch to nanocomposites, which can be seen as materials with elastic heterogeneities at tens of nanometer scale. And finally, there will be some conclusions. So what are phonons and why do we mind? So phonons are collective vibrations of a lattice, which can be described as propagative waves, and so they have a wave nature. They can be quantized, and the quasi-particle representing them is actually the phonon, so it has also a particle nature. It can have a very large frequency wavelength range, spanning from macroscopic down to sub-nanometric wavelength, and for frequencies from hertz to terahertz, so over many, many orders of magnitude. And depending on the range, it can carry different things like sound at very low frequency, and it's responsible for heat transport at room temperature at very high frequencies. So manipulating phonons means being able to manipulate the sound transport or heat transport for applications in acoustics, thermal management, and energy harvesting. So in crystals, phonons are, let's say, easy to describe. Because crystals are periodic and ordered, we can identify a unit cell, which can be described by 3 basis vectors, and which is then periodically reproduced in the space. This allows us to Fourier transform and to obtain the reciprocal lattice, which is the corresponding to the real space lattice, but in the reciprocal, that is wave vector space, where we will have as well a unit cell, the Brillouin zone, which is described by 3 basis vectors, and which will be periodically reproduced. So atomic vibrations are described in this reciprocal space. A phonon is characterized by a wavelength and or wave vector, an energy omega, which is related to the wave vector through a dispersion law, from which we can calculate the phase velocity and the group velocity, which is the slope of the dispersion. The phonon can be longitudinal or transverse, depending on the direction of the atomic vibrations with respect to the propagation direction, and can be acoustic or optic. So here you see an example of dispersion where we see the acoustic branch and the optic branch in an omega versus q space. And as you can see, the acoustic branch has 0 energy as 0 wave vector, while the optic branch has finite energy as 0 wave vector. What is interesting is that the acoustic mode has a very steep slope, which means a very large group velocity, while optic modes have usually negligible group velocity. So the energy transport will be ensured mainly by acoustic modes because they have this important velocity. So we can think of the phonon as carrying its energy with a certain velocity, which is the group velocity. And this is very efficient as far as the phonon is not scattered, but in fact, in real materials, it is scattered. So we can identify a typical time between 2 scattering events, which is the lifetime, and a typical distance between 2 scattering events, which is the mean free path. And these 2 quantities represent time and distance for efficient sound and energy transport. What now in a disordered material? In a disordered materials, things are more complex because we don't have periodicity. So we don't have a unit cell, no long-range order. Still, there exists a short-range order, as you can see here. Despite the disorder, collective excitations do exist, but phonon lifetime is much shorter than in a crystal because of continuous scattering from disorder. So what is interesting is that the dynamics in a disordered system will depend on the length scale. Indeed, if we have a very large wavelength, the phonon won't see the disordered structure. It won't see the atomic arrangement. It will just see the system as a continuum elastic medium. And at this point, it can really well propagate, and it will be a plane wave like in a crystal. This is the regime where the continuum approximation holds true, and the elastic theory applies. Then, when the wavelength gets smaller, the phonons at some point we start to see that the atomic arrangement is disordered, and then it will be scattered, and its lifetime will be reduced. So it's here that we will see the differences with crystals. And finally, when the wavelength becomes comparable with the interparticle distance, the phonon will see that there is a short-range order. At this point, its dispersion will be similar to the one of a crystal with the same local order, because it will depend only on the elastic constants between the atoms in this pseudo-unit cell. Now we are interested into this second range because this is the one where disorder will affect phonon propagation. This is this mesoscopic range, which is also the realm of vibrational and thermal anomalies. Here you see something which has been very long known, that is the difference in the phonon density of states between a crystal and a glass. The crystal has a density of states that at low energy goes like omega squared, which means that it follows the well-known Debye approximation. But in a glass, this is not true anymore. And this can be seen better if we normalize the density of states by the square of the energy. So in the case of a crystal, we have a flattening here, which is the Debye level. But in the case of a glass, we have an excess of states. This peak has been called the Boson Peak, and actually there are several theories on its nature, but I don't enter in this detail. What is interesting to know is that this excess of modes appears at a few terahertz frequency, and this corresponds to temperatures of about 10 Kelvin, where the thermal anomalies have been also observed in glasses. What do I mean by thermal anomalies? Is a peak in the specific heat with respect to the expectation T-cube behavior, and a flattening of the thermal conductivity with a plateau. So this boson peak has been considered as responsible for these anomalies. Now the question is, what happens to individual phonons in this range? In order to study phonons with terahertz frequencies, we need to use inelastic scattering technique, and in particular, I will talk about the inelastic X-ray scattering technique. This is a photon-in, photon-out technique where an incident beam with a given energy and wave vector interacts with a sample and it's scattered with a different energy and wave vector. From conservation laws, analyzing the scattered beam, we can derive the energy and wave vector of the phonon, which has been either created, either annihilated in the sample. Here you see a typical spectrum where we look at the scattered intensity as a function of the exchanged energy at a certain value of Q in a germanium single crystal. You see two peaks. This is actually the same phonon, once annihilated and once created. The energy position will give the dispersion law from which we can get the velocity, and the broadening will be inversely proportional to the lifetime. What now in a disordered material? In a disordered material, we find something like that. We have a huge elastic line, which comes really from disorder, but then we still have inelastic excitations. We can then define exactly the same quantities. The real difference is that the broadening now is much more important, being at least one order of magnitude larger than in the crystal. So with this technique, we have performed some 10 years ago a series of experiments on different glasses, and we have evidenced the existence of a strong scattering regime in the mesoscopic range. Here you see our pioneering experiment on glassy glycerol, where I've reported the phase velocity and the attenuation as a function of the exchange of the wave vector. As you can see, the phase velocity sharply decreases, then it describes a plateau, and then it joins this red curve, which would be the expectation for a crystal. At the same time, the attenuation strongly increases with Q, with the fourth power of the energy, and then it switches to a weaker dependence on energy, the second power. What is interesting is that this crossing point between the two regimes corresponds to the dip in the velocity, and it corresponds to the position of the boson peak. Moreover, if we calculate the mean-free path, we obtain a value which is smaller than the value of the wavelength of the phonon. This means that the phonon cannot be considered propagating anymore. And actually, this is what is called the Ioffe-Regel limit, which establishes the end of the propagative regime. Above this value, the phonons can be called diffusions because they don't propagate anymore, but they diffuse. We observed a similar phenomenology in other glasses, Like silica glass, you can see exactly the same thing, the dip in the velocity, the change of regime and the width, and everything at the position of the boson peak at the same temperature. In sorbitol glass, where you see the same thing, so the dip in the velocity and the two regimes in the attenuation. And it has been also reproduced by molecular dynamics calculations on a Lennard-Jones glass. So there is a distance scattering. The question is scattering from what? Actually, this scattering has been associated to scattering from local elastic moduli fluctuations. Indeed, in glasses, it is possible to measure it. The elastic constant fluctuates at the nanometer scale. So there is a distribution of elastic constant, and here you see it. This has been measured on a metallic glass, and you see on the nanoscale fluctuations in the color scale of the Young modulus. It has been also reproduced by calculations. So this is, for example, a calculation of the distribution of the shear modulus in a model polymer glass as a function of the coarse graining size. The smaller the size, the larger the distribution. So the idea is that these elastic heterogeneities scatter phonons, and they cause the strong scattering regime and the boson peak. And this has been reproduced by theories like the one of Schirmacher. So for glasses, we can say that at the mesoscopic regime, we have elastic heterogeneities. They cause the strong scattering regime, and so they cause the strong decrease of the mean free path. And for this reason, we switch from a situation where the mean free path is much larger than the wavelength, and then the phonon propagates well, and it's called propagons, to a case where the mean free path is smaller than the wavelength, and then the phonon doesn't propagate anymore, and we are in the diffusion case. Here you see some sketches of a propagative and diffusive motion of the atoms when we start a motion at the zero position of the sample. And now let's go to nanocomposites. A nanocomposite is a material made of the intertwining of materials with different properties at the nanoscale. The nanostructure introduces interfaces which are source of scattering for phonons, like you can see here, for example. And this is true in the matrix. For example, it's here we have a matrix with inclusions, but as well within the inclusion. Now, a nanocomposite can be thought of as a system with elastic heterogeneities because these inclusions are regions with different elastic constants. And so we find something very close to the glass case. When the wavelength is large, the phonon won't see the nanostructure and won't be scattered. But when the wavelength becomes comparable, of course, it will see the nanostructure and be scattered. So we expect a less scale dependent dynamics here as well. Here I present some theoretical results on the phonon propagation in nanocomposites, where we have evidenced the key role played by the elastic contrast between an inclusion and the matrix. This is a molecular dynamics simulation study on amorphous silicon with crystalline nano-inclusions inside. In order to change the elastic contrast, what we have done is to change the interatomic potential within the inclusion. We have used the Stillinger-Weber potential, which is made of a two-body part and a three-body part. And this three-body part has a dependence on a parameter lambda, which rules the rigidity of the system. Changing lambda, we change the Young modulus, so the elastic properties. And then we can change the elastic contrast, defined as the ratio between the Young moduli of the inclusion and the matrix. We have thus prepared a sample with no contrast and a sample with high contrast, where the inclusion is much harder than the matrix. Here you see the results on the density of states. This is the density of states for a plain amorphous material at room temperature in the normal and reduced units, and then you can see the boson peak. And when we go to the nanocomposites, we get this. In the case of no contrast, the density of states is very similar to the one of the plain amorphous material. But when there's contrast, we get high energy states because the inclusion is much harder. When we look in reduced units, we discover that in both cases, there's a change, the A rising of a low energy peak. What does this mean? To understand it, we have looked directly to individual phonons. We have calculated the phonons that you can see here in longitudinal and transverse case. And you can see every single peak is a phonon at a given wave vector. And you can see that going from the no contrast case to the contrast case, the phonons are still visible, but they get much larger. Much larger means that there is a strong decrease of the lifetime. And actually, this lifetime reduction happens at a wavelength of 2 nanometers, which is the interparticle distance. So when the phonon sees the nanostructure, at that point, it is strongly scattered. We have then calculated the phonon free path for the plane amorphism for the 2 nanocomposites. As you can see, there is a strong reduction of the phonon free path as soon as we put interfaces in it. And then another reduction when the contrast increases. But what is interesting is also that at the end of this calculation, which corresponds to the Ioffe-Regel limit, decreases. That is, the Ioffe-Regel limit decreases with the elastic contrast. Means that beyond this energy, there are not propagons anymore, but only diffusions. So in the case of a nanocomposite, the strong scattering at the nanostructural length scale reduces the mean-free path and reduces the propagative phase space, creating a pseudo-boson peak at the new Ioffe-Regel limit. In order to have further insight into this, we have investigated the wave packet propagation in a nanocomposite by finite element modeling. Here you see the typical sample with a series of inclusions aligned and then periodically reproduced. We have created a pulse, an acoustic pulse, at the center of the sample, and then we have let it propagate, and we have followed its propagation looking at the kinetic energy. Here you see some movies showing how our acoustic pulse propagate. Here you see the case of no elastic contrast. So you identify the front end of your wave packet, and actually you see that it propagates basically unperturbed. If we look now at the systems with a bit of elastic contrast, you see that you still can identify the front end, which propagates, but a lot of energy remains behind. This is a case of diffusive and propagative regime. That is, we still have propagation, but there's energy which diffuses a little bit everywhere. And if we look at the smallest elastic contrast, when the inclusion is extremely soft, we see that there's no propagation anymore, but the energy in the wave packet remain pinned on the interfaces and the inclusions since the beginning. So we can identify different regimes depending on the elastic contrast, but also on the length scale of the nanostructure with respect to the wavelength of the phonon. We can draw a map of these different regimes like we did here for a phonon of 7 terahertz frequency as a function of elastic contrast and dimension of the nanostructure. As you can see, small elastic contrast means propagative regime, and then increasing the elastic contrast, we go towards a mixed propagative diffusive and finally a diffusive regime. And at the extremes of this, we will go towards localization. Note that the 2 lines represent the 2 samples that we have looked at earlier. And in particular, this is a longitudinal phonon, which was this phonon here. We could not analyze it in the case of high contrast because it was extremely damped. So in conclusion, I've shown you with the glasses and the nanocomposites that when we have elastic heterogeneities, elastic fluctuations at different length scales, we can have a strong phonon scattering regime, which means a stronger mean-free path decrease. And this causes a crossover from a propagative to a diffusive transport regime. Now, I've shown you only the theoretical results from the nanocomposites for lack of time, but also because it is still ongoing, our experimental work confirming these predictions. It is important to underline that these effects make these nanocomposites promising for controlling sound and heat transport, because depending on the nanostructure, then you can localize, you can filter, you can deviate, and ultimately you can hinder or boost your transport. And that's all. I want to thank, to acknowledge all the people who's working with me theoretically and experimentally on the microscopic understanding of phonon propagation and thermal transport in disordered and composite systems. And thank you for your attention.